All right, so so when we've been talking about waves so far, we've been talking about essentially what comes down to transverse waves, right? We talk about waves on a string, we talk about a pendulum, or we talk about like a horizontal spring, anything like that. They've all been transverse waves in nature. Sound is different in that sound is a longitudinal wave. Okay, and the difference there is that, remember with a longitudinal wave compared to a transverse, the longitudinal wave, the disturbance travels parallel to the wave, right? So we saw when we did the Slinky lab, the Slinky would go like this, right, while the wave went that way, okay? In a longitudinal wave, I think some of you tried it just playing with the strings, right? You'd either take the Slinky and do this with it, right? Or you'd squeeze it really tight and then let it go and it would travel. And it looks pretty cool, right? Hard to see a little bit, right? Really hard to draw. Now you get the idea why it's like, it was tough for me, like, you're like, what is that thing? And, you were like, it is what it is, right? So essentially with a longitudinal wave, what you've got these two sections of the waves where you've got a thing called a compression. Right, that's when the things are really close together. That's when you took the springs and the coils got really tight, close together. But you notice that when one section got close together, the other pieces on the other sides of it had to stretch apart. Right? That stretched apart piece is called a rarefaction. Okay? So compression obviously makes sense. It's when they get squished. But a rarefaction is when they get pulled apart. All right? The way sound works is that at some point, what's going to happen is the air around whatever is vibrating, typically, right, whatever your disturbance is, right, it's usually some sort of vibration, it's going to cause the sound wave, the air around it to compress, right? What happens when you compress particles? The pressure goes up, right? Pressure goes up, and then at some point the pressure's like, I don't like this. The particle's like, I don't like all this pressure. And then they expand again, right? And that's your rarefaction. Well, then everything around the particles that just decompressed, right, or rarefied, they compress the ones near them, right? So that becomes that chain reaction, and that's how sound waves then travel, is that compression and decompression of air molecules as it travels or as it moves. Okay, does that make sense? All right, so what you would see in this really scientific drawing is that you would see air particles. If we're talking about a compression rarefaction, right, you would see something like this. Where you've got some particles that are really compressed, some that are spread apart, compressed, spread, compressed. Okay? That's essentially what the particles would look like in a sound wave if you were able to, like, show it. Yeah, right. And that's what it would kind of see. So you imagine. So when I drew it the first time, it was like, right, something like that. And now it makes sense, right? Now you see it, and then you're like, oh, I don't even know how I would draw that. And then you see why I have trouble drawing it. It's because of one, my lack of artistic talent, and then two, the hardness of drawing it, right? So if we were going to take this compression and rarefaction and put it into some sort of wave that we could look at, every time that there's a compression, that would be a peak. And everywhere where there's a rarefaction, that would be a trough. So what you would get for this would be, you'd get a wave that would look something like this. Okay, and that's what your sound wave would look like. Right, where you've got peaks are the compressions and rarefactions are the valleys. Right, so this would be your compression. And this would be your rarefactions parts. Okay? So essentially what you're looking at are regions of high pressure and low pressure. Okay? Makes sense, right? So the way we get things like this and we get them to do what we want them to do and use them is usually you have them run through some sort of object that can create the frequencies that you want to hear, right, or the frequencies that are produced. Excuse me. If you're talking speaking, right, your vocal cords vibrate the air inside of your, wherever they are, Come on, where's my AP Bio? Your larynx. All right, there we go. I was waiting for you, Spawn. All right. So and your larynx, and the vocal cords then vibrate the air around your vocal cords, which then creates compression rarefaction. It comes out your mouth, and then it goes to wherever you need it to go, wherever it's directed. Okay. So essentially, they're acting as how they vibrate is acting as that tube or whatever to produce the frequencies that you hear. A better example, and I think it's directly applied to physics and for like half this class, are musical instruments. So we're going to talk, and the big thing that happens in physics is they talk about different types of tubes. All right. So the first type of tube we're going to look at would be an open tube. Okay, and what an open tube means is that both ends of the tube are open. Wow. All right. What do you think a musical instrument that has an open tube might be? A flute, right? A flute. Right? A flute, it would be an open tube. Okay? So what happens in an open tube is if we were just going to draw this tube, imagine these are both ends that are open on the flute, okay? Both ends always need to end at an antinode. Okay? What is an antinode? Is that the peak or is that the spot that doesn't move? It's a peak, right? So both ends always need to end at a high pressure point. Does that make sense? Okay. So what you'd get, if we're talking about the first mode, right, the fundamental frequency, all right, what we would get is we would get a diagram that looks, or we'd get a thing that looks like this, right? And if I drew the other side of it like it was vibrating, right, we'd get something that looks like this. Okay? How much is that? How much of a wave is that? It's a half, right? It's a half a wave, right? Because it's like half of a peak and half of a valley. Does that make sense? Okay. So again, if we're going to use the idea again that we need to have it always begin and end at an antinode. Okay. So let's try the second one. Okay. And I need my colors. So if we're going to go here, we need like that. Was that going to get me what I want? I think so. Yeah, that'll get me what I want. If I do this one, it's okay. And this would be the second mode, mode number 2. So again, this would be what the wavelength divided by 2, correct? Right. This would be half a wavelength. How much of a wave is this? That's a full wave, right? So this would be a full wavelength for this one. Okay? So if we look at this, and let's just label this L. Just like a wave on a string, which we talked about last class, the boundary conditions are the length of the tube, right? In the last class, the walls or whatever the wave was connected to was the boundary condition. In this case, it's the length of the tube which is setting your boundary condition, and if it's open or closed. Okay? So if we look at this tube, right, do you think, can we come up with a relationship, just based on these two little things here, can we come up with a relationship which allows us to, one, predict the wavelength for any harmonic or any frequency, and then the frequency for any tube? What do you think? Is there some sort of relationship we can see here?
Yeah.
Okay. So how about for the wavelength? What would we get? What do you think? So for any mode, if we do the next one, how many waves am I going to get? If this is a half, this gives us one wave.
3 halves.
3 halves, right? 1.5 waves. Okay. So what do you think if I want to know any wavelength in relation to the length of the tube, right? What do you think it would be? Go ahead. So something divided by m. What's the something going to be?
L. No.
It's gonna be like mode of wavelength
Mode of wavelength divided by 2.
Because then it's like, okay, so first.
So m divided by 2?
Yeah.
Okay.
Because like.
But I want to put, that's a good idea, but I want to put it, but that wouldn't divided by 2. Yeah. Okay. But I want to know it in terms of L, right? 2L over m, right? So now, if I know the length of the tube, I can predict any wavelength, correct? So 2L over m. So this one, if this is half a wavelength, a full wavelength would be a length of 2L, right? If I put an put a mode of 1 here, right, that's going to give me the full wavelength is 2L, right? If I look at this one, where this is one full wave, is equal to, so a wavelength is equal to L, that means m would need to be 2, right? And that would give me then the wavelength is L, the length of the tube. Good with that? Okay? All right, so then now let's look at the frequency then. What's that? Velocity times 2L over m. All right, so we know, let's see, we know that v is equal to f lambda, right? Okay. Well, we know that lambda is 2L over m, right? So we could say then what, v is equal to 2L over m, correct? But if we put that in terms of the frequency, right, then the frequency for any mode is going to be v times m over 2L, correct? Now this is exactly what we know for a wave on a string, correct? Right? We learned this already, where this is exactly the same thing as a wave on a string.
Sound behaves similarly to
For an open. And similarly for a closed. Okay, if you have a closed tube, chimes, would they be closed?
There's an opening.
There's an opening on the bottom, right?
A triangle.
I don't know. I'd like to look up one day what is a closed.
Where's Jay?
But because honestly, you're going to get you'll see an open, and you'll see an open close. And we're going to talk about open close next. All right. So the open makes sense?
Drums. Yes, drums. 'Cause a timbre.
Okay. Good? We're good here? All right. All right, so for an open close system, you would have one end open, one end closed. All right? What do you think an instrument that's an open close might be? No, because those are strings. What's that? I can't hear you. What do you think? What might be, do you think, an open closed? Trumpet.
Really? Why?
A trumpet?
Oh, because your mouth seals the
How about a clarinet?
saxophone.
Right? Most of your reed instruments are open closed tubes. Right? Because in a trumpet, your mouth is the closed end. Right? In a clarinet, your reed is opening and closing the tube.
Wait, but then a flute.
In a flute, you're not actually putting your mouth up to it.
Oh, yeah, that's true. Yeah, it's just.
Right? It's just like resting on the mouthpiece. Okay? All right. So in this case, we keep the idea that for the open side, you need to start or end at an antinode. But for the closed side, it has to be a node. Right. Let me do it in a different color. Right? So it would be like this. Right? So you would get something like that as your waves. Okay? And this would be for m is equal to 1. How much of a wavelength do we have here? Right, so your wavelength would be what, 4L? It would be 4L, so we've got a fourth of a wave, right? Is what we've got, or a fourth of a wave is what we've got there. Okay? Look at here, we've only got half of a peak, half of a trough.
Oh, okay, I see. It's not going down all the way.
Right.
Gotcha.
If we do this, if we do another one, whoops. Oop. My computer would like to play better now. If we do the next one, right? We would start here. It would come down. Do the right colors. It's easier to see. Right? And we'd have that, and then we'd have something like that. How much is that one? That's 3/4 of a wave, right? Because you've got half of a peak and then a full peak, right? So this would be 3/4 of a wave. Okay, and this would be, I'm not going to talk about, I'll leave it at that, but it's not really the second. What's that? It's the third one, right? So, just like we found out up here, that this is 2L over M, what do you think this one is? 4L over M? Yeah, it's 4L over M. So for defined any wavelength, right, it's 4L over M. But here's the really important thing. This is really, really important. M can only be certain numbers. Right, 1, 3, 5, 7, they need to be odds. Can't be. Look at what we've got right here, right? This is 3/4. Okay? So the wavelength would be 4/3 or whatever, right? They have to come in quarters. Okay? They have to come in quarter intervals. Right.
So the mode is 2 on that bottom.
It's we would actually call it M as 3. That's why I was hesitant to write 2.
So
Okay.
M is 3, you plug it into there and you get 4/3
4/3 L would be the length of your wave.
would be lambda.
Right. So in this one, what can M be? M can be what? For the 1, 2, 3, 4, and all the way through, right? Okay. That's the big thing you need to keep track of when you're talking about open and closed tubes, is that open tubes it's 2L over M, open closed tubes it's 4L over M, and the M's have to be odds for an open closed. Okay? So when we get this, if we do the same thing, we would get the frequency of M is going to be what? V times what? M over 4L, right. Where again, M needs to be 1, 3, 5, and so forth and so on. The great thing that still works, in what you investigated last class, where you found that when you get a standing wave, the harmonics are multiples of the first of the fundamental, right? It still works here. So for an open tube, every harmonic is a multiple of the fundamental, and the same thing happens here. But again, it's 1, 3, 5. It's odd multiples of the fundamental. Okay? Does that make sense? So if you know one of the frequencies, you can find the rest of them. If you know which one you're looking at, or if you know it's the fundamental one. Okay? Does that make sense? Okay. All right, so let's move on to the next thing that's pretty cool. And it's fun to see, and it's exciting. No joke, it is. Beats.
Beats. Beats by 3 are the worst controllers.
Yep. All right, so beats. So let's, and they give a good example, and I think it was in high school physics book. Let's say you're playing the flute, and the person next to you is playing the flute. You're in tune. They're not. What do you hear? Fluttering, right? So I didn't know this. You can tune a flute. How do you tune the flute? Okay, I didn't know that until I just read that. I'm like, that's cool. I'm like, how do you tune an instrument that's a solid piece of metal? Evidently, it's not. So you hear that fluttering, right? And you say, all right, you're a little off. Someone's got to change, right? So with beats, what happens is you have 2 or more waves, right? Where their frequencies are close. they're close. All right? And you got the amplitudes are pretty much the same. We'll say they're the same. But the frequencies are off. But amplitudes? Yeah. Frequencies? Oh, I totally forgot to. I said it, but I didn't write it. So the amplitudes are the same, but the frequencies are just off. So let's say we want one person is playing 440. Whatever that note is. A. It's an A. Okay. All right. So Clarice is playing her. We know that her flute is in tune, and she's playing a 440, and she's shaking no like I'm never in tune. All right. And then we know that the person sitting next to you, who sits next to you? Okay, don't know who she is, but Victoria Scarfo is always in tune or not? She's always in tune, but today she's not. She's just not having a good day. Okay? And she's tuned to 442. Oh, what? What a jerk. All right? So she's at 442. Okay? So what you hear is a flutter, right? You hear like a woo, 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 right? It sounds like that. It's disconcerting, right? Okay? So what's happening is you're experiencing a thing called beats, all right? And what happens in a beat is it's constructive and destructive interference between the two different waves. Sometimes they're adding, sometimes they're subtracting, right? When you hear the high pitch, the boom, that is them adding. And when they're going down and they get quiet for a second, that's them subtracting. All right? And as long as you keep playing, you're going to hear that vibration in the sound. Okay? The way you can find out a couple things is, one, you can find out the frequency of the oscillation. Right? So what is it actually, the frequency you hear going whoomp, whoomp, whoomp as it goes through? And it's very simple. Right? So the frequency of the oscillation is just the average of them. Okay? So the frequency at which they oscillate. So if they gave you a graph and they said, what's happening with these frequencies, okay, and they could give you multiple graphs, you could say that the averages are different or the average changed, right? So the frequency of the oscillation, you could determine the frequency of the waves just by looking at the graph if you have enough information, right? And you can determine the rate at which that beat wave is oscillating. Okay? Yep.
So you said 2 or more waves, so like that frequency of oscillation thing, it could be like 1/3.
It could be, yeah. Typically we talk about 2, but
Okay.
I've done it with 3, and it starts to really get crazy. It's just what you hear. It sounds to get really odd. Okay? But if I want to know the rate of the beat, so I want to know the frequency of the beat itself, right? What's happening as it changes, all right? It's just the absolute value of F2 minus F1. Okay, so I want to know how much they're off by. We know it's that. Okay? It's just F2 minus F1. Okay? So it's pretty simple. So beats are really cool. They're actually relatively simple. But I guess it wreaks havoc on you if you're playing in an orchestra. Clarice is like, all right?